All right. So in this AP exam question, this is from an old AP exam, but this is a good question to show you because there's a bit of a wrinkle in here. Let's read the question. A tank with a rectangular base and rectangular sides is to be open at the top. Okay, so right away we have, you can draw this right here. You've got a rectangular top and bottom and sides. Don't know if it's a square bottom. It could be, but we don't know that for sure, so we're going to just draw it like that. It's to be constructed so that the width is 4 meters. I'm going to put the 4 there. And the volume is 36 cubic meters. All right. Okay, now we'll just pause right there. We don't know anything more about the construction of the box other than now that there's a cost involved in the second half. So let's just focus on this first half. Depending on what you want to do here with, I'm going to do length here and I'm going to do height here, okay? So I know that 36 has to come from the width times the length times the height. That's all that I know about the construction of this. That's what's given. That's what I can know. That's the first part. Now, normally, what you would do is you would say, and I looked at some of your work that you guys did already, and you guys said, all right, in order to minimize cost, we need to minimize surface area. And that is a very good thought, okay? That's a very, very good thought. The wrinkle is this, is that the base and the sides are not worth the same. There's a different cost involved there, right? It's $10 per square meter for the base. So this is $10 per square meter, and the sides are only 5. So let's use black here, okay? The sides right here are only 5. So the sides are cheaper than the base. Got that? So what that means is we can't, and on the AP exam, this is what they'll do. They'll say, hey, this looks just like questions that you've done. This is easy. Well, not that easy because there's a different cost involved. So if you just minimize the surface area, what you're doing is you're saying that all of the surface is the same. But we're not simply trying to minimize surface area. We're trying to minimize cost. So that means this, the base and the sides. So the base is more expensive. So if I can cheat a little bit on getting a bit of a smaller base than what would be totally optimized, I'm going to need to do that because it costs more. So whatever your optimum is for surface area, you're going to want to, that's going to have to be adjusted because the cost is such that you want your base to be a little bit smaller and your sides to be a little bit bigger. Now, how do we do that? Well, what you do is you say, okay, it's not just surface area that I'm trying to minimize, it's actually cost. And the cost comes from this, okay? $10 for the area of the base. And I'm just going to write it like this for now. And $5 for the area of the sides. Okay? So it is cost that we're minimizing. So I'm gonna get you to make your adjustment. You don't have to erase what you did, but I think that all of you probably will want to copy this down. It's a bit different than what I think you did that I saw. So let's flesh this out a bit. The cost is $10. Now the area of the base can be expressed with my variables here as 4L. You might have did this might have been X for you or whatever. So 10 times 4L. There's only one base. This one is $5 times, now the area of the sides is going to be what? I've got the area of the sides. Well, there's different sides, isn't there? There's L times H. There's 2 LHs. And I'm gonna make this all one expression, I guess. And there's also 2 what? 4 H's. Okay? So in this way, you kind of bring all of these constraints in, all of these sort of boundaries, right? We've got the cost is what we're trying to minimize, but the problem is I have 2 variables, right? So that's an expression for the cost so far, okay. But I want cost in terms of just one variable. So I've got L, I've got H. Here's where we now use this information, and I'm going to solve for H here. So this is 36 over 4L. Or that's 9 over L. H is 9 over L. Okay, you with me on that? Does that look good to you guys? Well, if that's the case, then I can rewrite this as this first term is 40L, no problem. This is going to be 5 times 2L times 9 over L plus, and this is a 2 times 4, isn't it? That's not 24. So that's a 8 times 9 over L. So this is now cost in terms of just L, just this variable length. Well, that's good. One variable. Well, let's simplify this here now. I'll try and keep that question in there for you. So C of L, 40L plus, okay, what do we got? These L's are gone. I've got 5 times 2 is 10 times 9, that's 90. And this is 5 times 72 over L. Ooh, okay. What's 5 times 72? It's 350, 360. Plus 360 over L. Am I doing that right in my head here now? 40 times 9, 360 over L. Okay. Okay, are we good so far? So what we need to do now, we can't gather any more like terms, but we need to take the derivative of C of L. Okay, so the cost function, we need to take the derivative. That's going to be 40 plus 0. And okay, so quotient rule, if you want to do that way, quotient rule, derivative of the top times the bottom, that's just 0, minus the top times the derivative of the bottom, so that's minus 360 over the bottom squared, L squared. That's minus 360 over L squared. Okay, so I just did the quotient rule on this guy, and you could do that over on the side somewhere if you want. Okay, it turns out to be minus 360 over L squared. So I've got the derivative. I, of course, want to find the critical number, or numbers, to try and find out where this cost is going to be optimized. So critical numbers are critical. So I'm going to let all this equal 0. Okay, so 40 minus 360 over L squared equals 0. And I'm going to have 360 over L squared equals 40. And move up over here. I'm going to have 360 over 40 equals L squared, because you can multiply both sides by L squared, divide both sides by 40. I've got 9 equals L, wait, what? 360 40, 40. 9 equals L squared. Okay, so L is 3. Whoops, L is 3. Okay. Awesome. Okay, that's nice. It's a nice even number. So what is, if L is 3, that is now going to be the optimal length. I have to find what the height is. I have to also find what the cost is. The question says, what is the cost of the least expensive tank? So do I, where's okay, so I have a cost function over here, right? That's just in terms of L. So I don't really need to find H. It doesn't ask for dimensions, I guess. Does it? Does it ask for dimensions? No. Just need to find the cost, right? Yeah. Yeah. Were you going to say something? Oh, is it frozen? I'm sorry. Okay, so L is 3, so we just need to find the cost. So so what I'm proposing here is that you don't need to find H. We could find H pretty quick. H is actually 3 as well, right? 9 divided by L. H is 3 as well. But the cost function, okay, here's the cost right here, right? As long as we did this right. If you want to go all the way back to here, you could, but whatever. We're trusting that we did these steps right, and you can just go to here then. So the cost, let's see. The cost should be, cost where L is 3, should be 40 times 3 plus 90 plus 360 over 3. So the cost where the length is 3, that's where this is going to be optimized, is going to be 120 plus 90 plus 120. So 240, 330. So the cost is $330. All right, so that should be your answer, $330. And the reason why we had to do it this way by integrating the cost in is because, again, the base is a different cost than the sides. So you kind of have to account for that. Here's the cost for the area. So we're kind of doing the area, but you have to split that area up and include the cost. So that's a wrinkle. We're not, the AP exam is not tomorrow. This is good news, right? There's going to be probably between now and then, we're going to spend another 50 or 100 hours doing this stuff so that you're ready, okay? You're all dropping the class now. Okay, but no, this is good. So, hey, you're going to get this, okay? Any questions about this one? Excellent.